Hello and welcome back to the lab. Today on the bench we have another shipment from PCBWay. They are not a sponsor of the channel, however they are who I used to do these boards, given some inexpensive cost and some good quality. So this is a continuation. This is actually part 2 of the building a power supply video. Obviously, for those that saw video 1, this is not going to fit the design requirement of into the same size package as a D-cell battery. However, I have some design elements that are going to change. So this is Rev3, and we're going to do some testing on this board to see how well we're doing with power supply design, things like that. It's a pretty simple design, but there's still quite a bit to consider. So we have a revision 3 board. This is a prototype. This was board revision 1, obviously drastically different, actually pretty much the same, spaced it out a little bit. Rev2 never actually made it to the board stage. Rev2 was like this, and we'll talk about some of the issues with this design in Rev2 that I moved some things around. So one of the things that was really important, and something told me, I'm not 100% sure what, but I had this all designed up and everything like that, and I ordered some parts. One of the parts I ordered was these from Mauser, which is a 1 amp 800 volt bridge rectifier. There's the part number for those following along. And that is this guy right here. And I had it wired up, given the way the schematic told me everything was, and something told me, hey, don't order the boards yet. Something's wrong. Don't wait for the rectifiers to come in. And as you can see, the pinout of the rectifier was slightly different. My positive was here, my negative was here, and my ACs were on this side. So this line had to move over here, and we had the AC coming off the transformer, and positive, negative there. This is the way it is done now. That kept me from having a pretty drastic PCB malfunction that I would have had to correct. The other thing that I really didn't like with Rev2, other than that, was for this resistor right here, which is just a bleed-off resistor for this capacitor. This is going to be a very high value, like a mega ohm or something like that, really high value resistor to bleed this cap down, because this cap is now huge for those that didn't see the previous video. This is a 10 millifarad capacitor, not microfarad, so 10,000 microfarad is what this cap's going to be. This is a Zener diode to keep the voltage, to keep this rail voltage from transiting too high. The Zener will kick in. This Zener diode is going to be a problem, and we're going to do some testing without it. I've also moved the Zener diode closer to the positive rail. So one of the design changes was taking the Zener diode from this side of the capacitor and moving it over to the output of the bridge rectifier so it can react a little bit quicker. Is a 3.3 volt Zener at 5 watt. This part's back ordered till 2024. So I'm still dealing with some pretty horrendous back order stuff, but we're working through it. So this moved to down here, and then pretty much everything that was here mirrored. One of the main problems was, especially for this resistor and the Zener diode, the loop area to get back to the negative, it would have had to come all the way around here, come all the way up, come all the way over here. So that's pretty extensive loop area. So what I could do, and the way the layout happened, is if I flipped everything, essentially mirrored it, I could cut the loop area so it didn't have to come all the way around the connector and then back to the negative point of the rectifier, so we could shorten up the loop area on all the components, which is always a good idea to do. So in this board, it's DC. We're not dealing with too high frequency stuff for here yet, but always a good design practice to have the least amount of loop area. Now, there's a lot of extra space in here, and my design target is still to get this in the footprint of a D-cell battery. So once we get through the testing and we've proven out the design and the board design and everything's working, all this is going to shrink. This is all going to come back, and it's going to shrink up closer to the transformer. And I'm even thinking about 90-degreeing the transformer, so instead of it being oriented this way, it's going to be oriented this way, so that puts everything in a line to compact it even more. There's a lot of space here for probing and things like that, and working around things and doing some experimentation and troubleshooting, which we are going to do as I put this together. I only have one transformer, so I'm going to have to be careful with making sure that jumps from board to board, because that transformer is like 36 bucks. So not a cheap solution, but a quiet solution. So first thing I'm going to do is I'm going to get the transformer wired up. I'm going to get it bolted onto the board. We're going to get the coil wired up. We are using the full size of the coil. We're not using split rail anymore. I was going to try to get away with a center tap in one side of the winding, but I didn't have enough go. And so I'm using both sides of the winding into the bridge rectifier. I want to measure what the voltage is, the AC voltage, coming out of the bridge rectifier before we put the capacitor in here. So, actually that's, yeah, it'll work, but it's not going to measure the way I wanted it to, of course. And maybe we'll throw the cap in and then do DC. Just see what the rectifier voltage is getting up to before we populate the rest of the board. So, actually, it might be a good idea, because this cap is so huge, to see if there's a charge constant. Yeah, let's do that. Let's put the bridge rectifier in. We'll put the cap in, and then we'll charge the circuit, let this thing run, and we'll see what we get up to before we populate U1, which is the voltage regulator. And then that will give us some information as to proceeding forward. Hopefully I can get away with this testing without the Zener diode, but if we have to put something in, we'll see what we can find. But as you can see, the mirrored components from the layout. This is not the layout that was sent to the fab. This was Rev2. This is Rev3. So I'm going to start getting Rev3 assembled. Okay, so for our first test, we have the transformer in place, the capacitor in place, and the bridge rectifier in place. Board's flipped over for ease of working on it. And we're going to plug this into the monitor. And where's the other end of the monitor? The other end of the monitor is plugged into the isolation supply, which is not hooked up at the moment. So we're going to come over here and plug it into the isolation supply over there. And we have zeros on the meters. I'm going to move you guys to the 6500 so you can see what's going on. Now, we have no load on it yet, but I am going to put a load directly across this capacitor. So this is going to give us an idea if that diode bridge and capacitor combination can keep up with our 300 milliamp draw. So, we are measuring DCV. Let's give it some gas. And as the line voltage climbs, so does the voltage across the capacitor. And right there, we're at 223 volts, which is usually where the lab sits, and we're at 3.17. So that's actually really good for that regulator. That's safe on that voltage regulator. So let's add a 300 milliamp load. No, not 300 amps, 0.3 amps, 300 milliamps. There we go. So we're going to turn the load on, and we'll be able to see what goes on down here. So with the load on, we drop down to 2.2. Now, bear in mind, we're looking at we need a rectifying voltage of I think it's 1.7 because it's a 1.5 volt rectifier. So this 2 volts will work, maybe, but it's a really good shot. So let me get the rest of the board populated. We'll shut the power supply down. Let's see how long it takes to charge with the load on. Not long at all. So very nice. Okay, so the nice thing about this is the load discharged the capacitors for us. We will unplug this for safety, of course. And now I have to finish populating the board. Okay, we have the board populated. Everything is working. The other thing to keep in mind is this is all prototyping. Like all this is not how a final product is assembled. These would all be cut to length, go right into the board, shortened up. Due to this being prototyping, I left these long. I know this is probably triggering to some people. It's triggering to me too, so don't feel bad. But let's fire this up, and then we'll swing some voltages and see where our regulation starts and stops. Because that's another one is I need to be able to handle above 120 volts and below 120 volts. So for my 240 friends in other areas of the world, different transformer, everything else should be fine. Okay, our probing methodology is I have the DMM 6500 hooked up to the bridge rectifier. That's going to show me what's going into the capacitor. I have the load hooked up to the external side of the voltage regulator with the 2 stabilizing caps next to it. So let's fire up some equipment and do some testing. Well, the good news is I have not blown up my regulator. I'm at 123 volts AC. No load. The load's turned off. I'm getting 1.493 out of U1. So, and I have 3.2 volts on the capacitor that's coming out of the bridge rectifier. Let me wind this up a little bit, and I want to see what the cap goes up to. My voltage limit is actually going to be U1, not the capacitor. Capacitor is 6.3 volts. This is 3.6 volts. So let's dial this up to 130 volts AC and see where we go. So I am at, let me show you guys what I'm looking at. Now bear in mind this is worst case scenario for U1 because the load is not turned on. There's no load on it at all. Okay, I'm at 131 volts line voltage. We're currently drawing 25 milliamp, but the load's not turned on, so that's the quiescent current. I'm at 3.617 on the capacitor. So this right here is about where I want that Zener diode to be in the circuit because it's starting to push the upper limit of that voltage regulator. So I want something to bring that down, but I need it to be active so when it's under load, it's not dragging the transformer down and I'm losing capacity. If I turn the load on, we do this. Pardon the camera movement. So here's our 1.46 volts coming out of U1 at 299 milliamps. So we got a full 3 milliamps of draw. Let me show you what the capacitor did. Here's the DMM 6500 at 2.3 volts, nice and regulating. Everything is fine. If I turn off the load, oops, you'll see this jump back up to 3.6 volts. The lag is the charging of the capacitor, but it will eventually settle off. So everything is looking really good. Definitely don't want to push the voltage up too much higher without the Zener voltage. So next test would be, let's turn the load back on at full load and dial back the line voltage and see where we fall out of regulation. All right, here we are looking at the regulator. I'm going to start pulling line voltage out. I'm doing this with the Variac and the isolated supply, so we're going to start dialing this back. We're going to see instant changes with because we have a 300 milliamp load coming through this. So we're starting to fall out of regulation right about there. So we'll call it 4.5 is when the regulator's starting to struggle a little bit with regulation. Let me show you where everything else is. So our voltage across the cap is 1.64, which is in spec for U1, because remember, U1 needs 300, I think it's 300 microvolts above for regulation. I have to look at the data sheet. I'm not sure. But we're at 164, we're at 146, and this is at a 300 milliamp draw, and this is going in a meter. If I dial this to 50 milliamps, plenty. So this is at the I'm testing it at the extreme end of what the regulator can provide. I don't expect a VTVM to draw 300 milliamps out of a battery. It's going to sip current. It's not going to yank 300 milliamps. So at 50 milliamp, at 300 milliamp, we got down to about 109 volts before we lost regulation. So let's see how far it goes at like a 50 milliamp current draw. So we said 146 is out of regulation. Passed it a little bit. That's okay, we'll dial it back up. And 146, there we go. At 50 milliamps of current draw, capacitor voltage of 1.7, that's what's coming out of the bridge rectifier. However, under 90 volts of line voltage. This is fantastic because that gives me a lot of headroom in this transformer. Obviously, if I yank on a 300 millivolts at 90 volts RMS in, it's not going to play nice. But at least for me, and in my area of the world, my lab's running at like 123. And I know the power company's trying to keep it above 117. So we have a decent amount of play here, and the ohms range in a DMM is also adjustable for a dying battery. So as long as we're not burning any circuits up, nothing gets unstable, this can live there. It's not drawing too much current. The transformer is rated for an amp. My U1's going to die at 300 milliamps, so, and I believe even U1 is short protected, which is the regulator. So everything is looking good. I'm going to let this cook in the lab. I want it to run. I want the load to be on it. I just want to see if anything gets warm. U1 is dead cold to the touch, not even feeling anything. So the copper pore layer on the board is doing its job, soaking the heat out of U1, doing a couple other things. So not unhappy with the performance of the circuit. Everything looks like it's going well. Definitely had a capacitor problem in the last one. So I'm going to dial this back. I'm going to plug this into the mains, unprotected. Well, fused, but off the isolation transformer, so we'll be good to go. It should be noted that this circuit, especially using the transformer, this side of the circuit, which my hands are nowhere close, even though it looks in the camera, this side of the circuit is at mains potential, at mains current. There's, right now, because it's on my isolation supply, there's current limiting and a whole bunch of other things. So if I plug this into the wall, it's 15 amps at these wires. If you're uncomfortable building something that's mains powered or you don't have enough experience working on mains electric, please, please, please do not build this and get some help. Electricity is very unforgiving, and, well, just that, it's very unforgiving. Once can be enough. So, as always, take care. In this particular circuit on this side, we're at 1.53 volts, very low voltage. Danger side. So we are building a power supply designed to go into a VTVM and be powered off the mains to replace the battery in the VTVM. So that being said, I'm going to let this cook on the bench for a while, make sure we don't have any problems. I'm going to run it high, run it low, do some extensive testing before I sign off on this and say, hey, the design is good, go ahead and build it. Do not build this yet. I did not say the design is good, go ahead and build it. It's still in the testing phases. I also need to shrink it significantly pull the voltage regulator back, move the cap back closer to the transformer. This could shrink down quite a bit, especially for being surface mount. So I'm not going to get a surface mount cap that big though. Everything is good to go, and we are cruising. I also want one of the tests that I'm going to do on this is I'm going to run it at 130 volts at 300 milliamps load, and I'm going to let it bang on it for a while, and we'll see what happens. Don't want to go too much over 130 because I don't have the Zener in there yet, but time will tell. One other thing to note, here's some test conditions of the power supplies plugged into the mains. I have 122.1 volts on the input to the transformer. I'm at 3.35 going into the capacitor with the board as is. So the cool part about that is, because I was planning on using a 3.3 volt Zener, the Zener, as long as it's not a transient overvoltage, it's not going to be doing much in circuit because of the way it's just going to be waiting to absorb some overvoltage if there's a surge on the line or something and it goes way high for a second during a power surge. So biggest thing is I'm going to need that discharge resistor because that's one really big capacitor. Okay, after a night of moving loads around, adjusting the draw current as well as dialing up and down the line voltage a little bit, everything was nice and stable. I couldn't get the board to air out. Everything also stayed dead cold. The warmest thing on the board was actually the rectifier bridge. The regulator stayed nice and cool. Everything was good to go. So might even add yet more capacitance to this circuit. Let me know what you guys think in the comments below. Is it good enough, or should we add even more bulk storage capacitance to this? I don't know. But where we're at right now is we know the circuit works. This board is obviously a prototype, and I need to shrink it, but everything is working. Now I just need to get the circuit in the form factor that I wanted and get some additional components. So there will be a Rev3. I've posted this on Patreon for people to look at. I've even released the design files up there, the entire KiCad repository for this board, if anybody wants to play with this as well. Maybe adapt it to a different purpose, but I have not released a BOM sheet yet, but I'm getting close to that, bill of materials. And but everything's coming along nicely. So a little bit more design work, and the next time I put this in front of the camera, we will try to fit it in a physical package of a D-cell or C-cell battery. So I'm going to play around with that and see if I can't get the layout to be a little happier with within that physical space limitation, so we can shoehorn this into some VTVMs. One other thing to note is during the testing, we did have some power outages and all kinds of utility and mains weirdness. So this board has even survived having some power outages coming back on, things like that. So very happy with the design. Everything kicked up the way it was supposed to, and everything worked. With that, I hope everybody enjoyed. Take a look at the comments below. I'll be there between every video. If you like what's going on, like, subscribe, and share, and I will see everybody in the next video.